Okay, hello Year 13s. This is just a short video on inverse trig functions. Now, you have actually met these before, and exercise 6b, where we go over this kind of idea, is a very short exercise. It wouldn't even take a whole lesson. It will only take half a lesson. So this is just a few things I want to mention. It's almost one of those topics I might even skip over. In the past I've skipped over it because it's like, well, there's not much in there. But the one thing you want to be aware of actually is how to draw the graphs. But the first thing I want to say is you've met inverse trig functions in year 9, yeah? When we do things like sine to the minus 1 of, let's actually write down something like, in year 9, you might have had like sine x equals 3/5. Well, when you try and solve that, and you do x equals inverse sine of 3/5, that is an inverse trig function, yeah? So you've known about inverse trig functions for a long, long time. This should not be a new thing using them. You apply an inverse sine to undo sine, yeah? And you've been doing that for years. If you like on your calculator, it's shift sine. Well, in A level, they kind of rebrand it, yeah? You know, when you rebrand something, you don't really change it, you've just given it a new name. Well, inverse trig gets rebranded in A level. We call it arcsin, arccos, and arctan. Now, that is sine to the minus 1, cos to the minus 1, and tan to the minus 1. They're exactly the same thing. So this is just an old idea made new, yeah? So sine to the minus 1 of x, I'm just going to point out that we sometimes call that arcsin x. Cos to the minus 1 of x, or inverse cos of x, well, that's arccos x. Oh, I almost missed out the C on arccos x. And inverse tan, well, that's arctan. Exactly the same thing. Now, there are some interesting things we can say about this, though, especially now you've all done range and domain. You'll notice that when you do inverse sine, yeah, or shift sine, when I'm doing this with my classes anyway, let's say we solve sine x equals a half, yeah, for 0 to 360. Well, when we solve that, our calculator only gives us one of the answers, doesn't it? And the reason our calculator only gives us one of the answers when we arcsine a half, and that's what we're doing, we're taking the inverse sine of a half, we're arcsining a half, is because the calculator understands that inverse sine is a one-to-one function, even though sine x is a many-to-one function. You see, what a calculator actually does is it restricts the domain of the original function so that the inverse, which is arcsine, exists. Because calculators can't spit out infinite numbers of answers. They can only give you one answer, and that's why we have to do our rule of thumb for sine, which is where you do 180 minus 30, well, that's 150, and then you can, find all your other answers by adding multiples of 360, so on and so forth. So inverse sine or arc sine is, it will just give you one answer, and as a result of that, let's talk about the graphs. Okay, let's say I'm trying to draw inverse sine of x, y equals, and let's call it what it is, arcsine of x. Well, to do that, I'm going to really have to think about what the graph of sine x looks like. Now, let me just quickly show you sine x. And I'm doing this on here because my graphing skills aren't that great. Here's sine x. You'll notice that this is in radians, and that's why it's going through pi there, or 3.14152 pi there. Now, do you also recall, I hope you do, that inverse functions, graphically speaking, they are a reflection in the line y equals x. That's what we're going to try and do. We're going to try and reflect this in the line y equals x. Now, you might be thinking, it's now going to like snake along the y-axis all the way up and down. That's really good thinking. I like the way you're thinking there. But, like I say, in order for this to be a proper function, we restrict the domain so that the original function, y equals sine x, becomes 1-to-1. Now, the most sensible way to restrict that domain would be to make sure it only goes from minus pi over 2 up to pi over 2. Then it would be a 1-to-1 function, yeah? Because if you were to draw a horizontal line across, it would only hit the curve once if you make sure it only is defined from minus pi over 2 up to pi over 2. That makes it a one-to-one function rather than a many-to-one function. It's many-to-one because if we draw a horizontal line, it hits that curve, an infinite number of times. So two things we're going to do here. We're firstly going to restrict it, the curve, so that it's only going from minus pi over 2 up to pi over 2. And then we're going to reflect it in the line y equals x. Now, I'm not sure, actually. I might be able to do it on GeoGebra, but it'll probably take me a little while figuring it out. So let me just ask you, if you can, could you just ignore the curve after there, going on all that way, ignore that bit of the curve and ignore this bit of the curve, because we're going to ignore that. It's only defined from minus pi over 2 to pi over 2 to make it one-to-one. And then we're going to draw it. So what we're going to do, what the graph's going to look like, let me actually draw it here. Now I'm going to draw sine x in a particular colour. I'm going to draw sine x in blue, I think, the original sine x. So this is the original sine x. But I'm only going to draw it from minus pi over 2 up to pi over 2. It's going to look something like that. Yeah, or if you like in old money, minus 90 to 90 degrees. Yeah, that way the sine function is now definitely one-to-one. It's not many-to-one, because you have to do that for the inverse to exist. Now, one of the things I have done, which I'd like to actually... I'd like to just try and draw that again, because at 0 the gradient should be 1 on this graph. No, I think I've made it look a lot more steeper than it actually is. And that's why this is actually quite tricky to draw. I've done this mistake many, many times. Okay, so let's just try and improve that graph a little bit and draw it more like this. It's going to be more very good. And on a graphical tablet, it's even worse. So apologies for that. It looks something like that. And then the line y equals x, well, because I know the gradient of sine x is 0 at the origin, the line y equals x is going to look like this. So that's the line y equals x. And now I can reflect that in it to find out what y equals arcsine x looks like, because it is merely an inverse function. So arcsine x, if we can do this in red on this diagram, yes, it's going to be in red, and I'm going to show you a much nicer picture on GeoGebra after this, so don't worry. Okay, it's going to look something like this. It's going to come in here, and then it's going to go like that up there, yeah? And the interesting thing about the inverse function is all the x and y values swap over. The range and domain swap over, don't they? So this is now going up to pi over 2 and down to minus pi over 2. And here it will be up to 1 and down to minus 1, yeah? Because on the blue graph, if I go back to blue, that's going up to 1 and down to minus 1. Now, I haven't drawn it beautifully there, as you can see, but I've done my best. It's tricky to do. Here's a much better picture of it on a graphing software package. Okay, let's just type in y equals arcsine x. I think they do arcsine. Yeah, there we go. Okay, you can see GeoGebra, clever old GeoGebra, actually knows that it's only defined for those values, and so you get basically a reflection of y equals sine x in the line y equals x, but it's just for the values of minus pi over 2 up to pi over 2. So you can see it goes up to pi over 2 and down to minus pi over 2 on the y-axis, where it's between minus 1 and 1 on the x-axis. And that is the graph of y equals arcsine x. It's why I want to show you this video, really. It's the graphs, once again, which can be the trickiest bit to go through. Okay, so what about y equals cos x and y equals arccos x and arctan x? Well, exactly the same process. We'll leave y equals x there, but we'll draw this time y equals cos x. And I think this is harder to draw, really, because you've got to try and now cos, we don't do it from minus pi over 2 up to pi over 2 because we'd be missing some of the function, yeah? So the sensible way to do it for cos is to define it only from 0 up to 2 pi, yeah? That is how we make cos one-to-one. So we're only going to be going from there up to there. Yeah, and it says all this in the book, so by all means do read through the textbook and you'll see what I'm getting at. If I now type in y equals arccos x, or if I now try and reflect that in the line y equals x, that's what you get. Now let me just pull it back because it's going off the page. That's hard to draw. If you imagine like this part of the graph being ignored, and also the part after pi, which is from here being ignored, the blue line is being reflected in line y equals x, generating the green line. You'll notice this goes from 1 to -1 on the x-axis, because before that was on the y-axis, and it goes from 0 to pi up here. Yes, did I say 2 pi before? It's actually just from 0 up to pi to make it a one-to-one function. I think I said 2 pi. That's definitely wrong. It's just from 0 up to pi. Okay, and that is arccos x. For arctan x, well, once again, exactly the same idea. Draw the tan x graph. And it looks like that. Now we're going to ignore most of this. We're going to be working just from -pi/2 to pi/2. So ignore this blue line up here and down here and over here. We're just looking at the central blue line, if you like. Let me just put it in the center of the screen. So ignore the extremities over here and over here. Equals arccos x, and it should arctan, sorry, and it should be a reflection in the line y equals x, and sure enough, there it is. Not between 1 and -1, just as tan is not trapped. The domain here is, it can be anything, and then it's just going to be flying off, yeah, in both directions. It's a nice little reflection. Okay, and that is y equals arctan x. Now, the solving in the exercise doesn't really scare me at all. For example, I'll do 5-part C if you like, if that kind of thing freaks you out. It's something actually you can do with a calculator. So this is just one question from the exercise. It says solve, and this is the last thing I'll do. It's the graph sketching though which scares me. If that pops up in the exam, it can be really quite tricky. Just remember, you've got to reflect sine, cos, or tan in y equals x, but restrict that domain. Okay, so we get cos x equals sine of arctan 1 over root 3. It's just inverse tan, remember, plus arccos a half. Okay, let's give this a go then. Okay, so cos x equals sine of, now you can work out a lot of that, arctan of 1 over root 3, it would be 30 degrees. It's inverse tan of 1 over root 3, which is 30 degrees if you're in degrees, but we're in radians, we're grown-ups now. Inverse cos of a half, that would be 60 degrees, or, in our case, pi over 3. So we've got cos x equals sine of pi over 6 plus pi over 3. That's sine of pi over 2. Sine of pi over 2 is 1. So we've actually got to solve cos x equals 1. And we can certainly solve cos x equals 1. It's 1 at 0 and 360. So the solving equations aren't too bad. So that exercise 6b, it's not too bad. Do half the questions in 1, half the questions in 2, then do 3, 4, 5, and 6, and you should be fine. Okay, best of luck with that, and I will see you very shortly with a compound angle video. Bye-bye.